A crew of astronauts is visiting a newly discovered planet of mass 9.6 times 10 to 19 and a radius of 6,400 meters. While on the new planet, they have decided to investigate the principles behind simple harmonic motion using a pendulum. Their pendulum is attached to a 5 meters off the ground, where that 5 meters is pretty insignificant for the 6,400. And then there's a length of rope that is 3 meters long. So that 3 meters long, that will be the length of the pendulum, the L. The pendulum bob has a mass of 20 kilograms. So we've kind of identified the important information in this, and maybe we've over-identified just a little bit, but at least we know everything that they've given us thus far. We need to identify which variables will affect the pendulum of which variables will affect the period of this pendulum, that is. Well, how do you calculate the period of a pendulum? The period is 2 pi times the square root of L over G. Well, 2 is a number. Pi also represents a number. So the two variables that will affect the period of a pendulum would be L, the length of the pendulum, in this case 3 meters long, and G, the acceleration of gravity on that planet. If we're not told otherwise and we're on Earth or near Earth, we'll use 10. Calculate the gravitational field G that will act upon the pendulum when it is positioned on the surface of this planet. The acceleration of gravity, little g, is calculated as big G times m over the radius square, or the distance squared between center of mass to center of mass, so middle of planet to the pendulum. Big G is the gravitational constant, 6.67 times 10 to the minus 11. They gave us a mass of, or I'm sorry, the mass of the planet is 9.6 times 10 to the 19. Again, those extra 5 meters or whatever it is off the ground is insignificant when we look at the entire mass of the planet, distance, all of that. And of course, the mass of the pendulum bob doesn't even matter. It's not in the formula. Radius is 6,400. So we have 6.67 times 10 to the minus 11, gravitational constant. We'll multiply it by the mass of the planet, 9.6 times 10 to the 19, and we're going to divide that by the 6,400 squared. The biggest problem or the biggest mistake we'll probably have here is not squaring the distance or the radius. Make sure you square that. Once we put that in a calculator, we get about 156.33 meters per second square for the little g, or acceleration of gravity. Calculate the period of oscillation for this pendulum, assuming it begins at 20-degree angle away from the pendulum, the equilibrium point. There's nowhere to put the 20-degree displacement or how far you pull it back. It doesn't matter. It's 2 pi times the square root of L over G. So we've got 2 pi times 3 divided by, or 2 pi times the square root of, 3 divided by 156.33. When we put that in our calculator, we're going to get 0.87 seconds because periods are measured in seconds. Don't let the extra information confuse you. One of the astronauts states that the bob always has acceleration even when it's at maximum amplitude and when it's at the equilibrium point. Is this correct? It does not specify what kind of acceleration. So don't be narrow-minded and say, oh, well, there's no acceleration at equilibrium. Well, it's still moving in circular motion. When it's at the amplitude, we have zero velocity. That's where it's changing direction. So at amplitude, we still have a restoring force that is accelerating it back towards equilibrium. When you get to equilibrium, no more restoring force, no more tangential acceleration. But at equilibrium, you have max velocity. This object is moving in a semicircle, so it has circular motion. At max velocity, v squared over r is our centripetal acceleration. So they're inverses of each other. Centripetal acceleration and tangential acceleration are inverses of each other. So you always have one or the other or some combination of both. As you're approaching equilibrium, tangential acceleration's going towards zero. As you're going towards equilibrium, centripetal acceleration is becoming its maximum value. So yes, there is acceleration through the entire motion. As max amplitude, there is a tangential acceleration pointed towards equilibrium. The restoring force causes this acceleration. At equilibrium, the tangential acceleration is zero, but the velocity is maximum, which gives you that calculation for centripetal acceleration. Second page. A block of mass 3 kilograms is hung from a spring, causing it to stretch 12 centimeters at equilibrium. The 3 kilogram block is then replaced by a 4 kilogram block, and the new block is released from the position shown above, at which the spring is unstretched. In the picture, it's unstretched, is what they're saying. How will the spring's equilibrium position of the 4 kilogram mass compare to the equilibrium position of the 3 kilogram mass? Explain your reasoning. On an FRQ, I'd really want you to write this out in words, but I wanted to demonstrate in this question, where's the information coming from? So let's first determine what the spring constant is, because what we see is the displacement is 12 or 0.12 meters. We know the mass is 3. We know the acceleration of gravity is 10 when we're on Earth. So the spring constant itself is going to be what? 30 divided by 0.12? So 250. Now that spring constant doesn't change. So now if we have a new displacement, we would have our 250 spring constant times x is equal to mg, the new mass being the new m, 4 times 10, so 4d. So 4d divided by 250 will get us our new displacement. When we calculate that, we'll be able to say emphatically what's going on with the proof with the numbers. Again, I wanted you to see where it comes from, but the ideal answer is going to talk about when a system's in equilibrium, we have balanced forces. If we increase the mass, we're increasing the downward force with force of gravity. In order to balance that, we have to increase the force of the spring. Well, how do you increase the force of spring for a spring that hasn't changed? Because the K is constant. Well, we have to increase the displacement from the spring's equilibrium, that X. How do you increase the X? The spring is stretched further. So balanced forces means, or equilibrium means balanced forces. If we increase one, we have to increase the other. In order to increase force of spring, we just simply increase the displacement. That's an easy way to summarize. But again, I wanted to show you this problem worked out completely so that you can actually see where does it come from, what's the mentality behind it. But certainly we want to answer in words. Number 2 asks us to calculate the period for the oscillating 4 kilogram block. So we know that period for a spring is going to be 2 pi times the square root of m over k. Well, k we calculated for number 1. So we have the k is 250. The mass is 4. So we have 2 pi times the square root of 4 divided by 250 in order to calculate the period of this system with the 4 kilogram block on it. Four divided by 250, take the square root of that value, then multiply by 2 pi. That gets us 0.79 seconds, because again, period is calculated in seconds. Now they've given us a big table Looks like they varied the mass, and with each mass they'd had two trials, and they're comparing the velocity to the mass and the kinetic energy from that. And it says, based on this data, derive a formula to calculate the kinetic energy. So we want a formula to calculate kinetic energy from a known mass and a known velocity. Sorry, don't we already know that formula? Kinetic energy is equal to 1/2 the mass times the velocity squared. If we know the mass and we know the velocity, we can use that formula to calculate the kinetic energy. That wasn't so bad. A lot of information for such an easy question. A student wants to test to see if the length of a vertical spring affects the maximum velocity of an object oscillating at the end of the spring. Propose an experimental design by which a student could test this. So they're saying, okay, well, if the spring is longer, is that going to affect anything as far as the period's concerned? Or is that what it asks? Propose an experiment by like the spring maximum velocity. Oh, is it going to affect the maximum velocity? Well, we know the period's going to be the same. And if the period is the same, it's got to be the same time period to do a full lap. Well, if you have a longer distance to cover, you would think you would have to move faster. Longer distance, faster, shorter distance, slower. So what we can do is we can find a device that can measure or capture velocity. So if we use some sort of motion sensor, motion detector, radar, photo gate, anything that we can use to calculate velocity at equilibrium. And of course, we can do this multiple times, and then we can use multiple springs, but they need to be made of the same composition, the same thickness. We want them to have the same constant, because the only thing we want to isolate the length as being the variable that we're testing, not anything else. So then if we're able to have everything the same except for the length, and then we measure the velocity at the equilibrium, that would help us calculate this and see if, in fact, what the data would look like.